Download this code from codegive.com, link in the description below. OK, let's dive into Chebyshev interpolation and rational approximations. This is a powerful set of techniques used for approximating functions, often achieving high accuracy, especially when dealing with functions that might be challenging for standard polynomial interpolation. Introduction, the essence of approximation. The goal of approximation is to find a simpler function, example a polynomial or a rational function, that closely resembles a more complex function over a specific interval. This is crucial in numerical analysis and scientific computing for several reasons. 1. Computational efficiency. Evaluating a simple approximating function is often much faster than evaluating the original complex function, especially within loops or iterative algorithms. 2. Representation and storage. Approximations can provide a compact representation of a function, requiring less storage space. 3. Differentiation and integration. It's often easier to differentiate or integrate an approximating function analytically or numerically than the original function. 4. Modeling and analysis. Approximations can reveal key properties or behaviors of the original function that might be obscured by its complexity. 2. Chebyshev polynomials, the foundation. Chebyshev polynomials are a family of orthogonal polynomials defined by the recurrence relation. T sub 0 / sub x equals 1. T sub 1 / sub x equals x. T sub n plus 1 / sub x equals 2x. T sub n / sub x, T sub n 1 / sub x, for n greater than or equal to 1. An equivalent definition, and the one that provides better insight into their properties, is using the trigonometric identity. T sub n / sub x equals cos n arcos x, for -1 less than or equal to x less than or equal to 1. Key properties of Chebyshev polynomials. 1. Orthogonality. The Chebyshev polynomials are orthogonal with respect to the weight function w, x, equals 1 / sqrt, 1, x sub 2 / sup, over the interval -1, 1. This means indefinite integral sup 1 / sup sub -1 / sub t sub I / sub x, t sub j / sub x, /sqrt, 1, x sub 2 / sup, dx equals 0, if I is not equal to j. 2. Range. T sub n / sub x, takes values between -1 and 1 for x in -1, 1. This bounded behavior is important for error control. 3. Equioscillation. T sub n / sub x, has n plus 1 extrema, maxima and minima, within -1, 1, and the absolute value of the function at these extrema is always 1. 4. Leading coefficient. The leading coefficient of t sub n / sub x, is 2 sup n 1 / sup, for n 0. 5. Roots. The roots of t sub n / sub x, are given by x sub k / sub equals cos 2k 1 pi / 2n, for k equals 1 2 n. These are known as Chebyshev nodes of the first kind. 6. Extrema. The extrema of t sub n / sub x, are located at x sub k / sub equals cos k pi / n, for k equals 0 1 2, n. These are known as Chebyshev nodes of the second kind. Why are Chebyshev polynomials important for approximation? Minimax property. The scaled Chebyshev polynomial t sub n / sub x, /2 sup n 1 / sup has the smallest maximum absolute value among all monic polynomials, polynomials with a leading coefficient of 1, of degree n on the interval -1, 1. This property is crucial in minimizing the maximum error of a polynomial approximation. Asterisk clustered nodes. Asterisk the Chebyshev nodes are clustered near the ends of the interval -1, 1. This clustering helps to mitigate the Runge phenomenon, which can occur with equally spaced nodes when interpolating high-degree polynomials. Runge phenomenon is the oscillation that happens at the ends of the interval when interpolating with high-order polynomials. Chebyshev interpolation minimizes it. 3. Chebyshev interpolation. Chebyshev interpolation involves finding a polynomial that interpolates a given function f, x, at the Chebyshev nodes. The resulting polynomial is called the Chebyshev interpolant. Steps for Chebyshev interpolation. 1. Transform the interval if the function f, x, is defined on an interval a, b, transform the interval to -1, 1 using a linear transformation. X equals 2t, a, b, /b, a, where t set membership symbol a, b and x set membership symbol -1, 1. F, t, equals f, x asterisk, b, a, plus b, /2. To calculate Chebyshev nodes choose the number of nodes n. Calculate the Chebyshev nodes of the first or second kind in the interval -1, 1. The choice between first and second kind depends on your specific application and error requirements. First kind, roots x sub k /sub equals cos, 2k, 1, pi /2n. Second kind, extrema x sub k /sub equals cos, k pi /n. 3. Evaluate the function evaluate the function f, x, at the Chebyshev nodes x sub k /sub. Let y sub k /sub equals f, x sub k /sub. 4. Determine the coefficients find the coefficients of the Chebyshev interpolant. The interpolant is expressed as p, x, equals a sub 0 /sub 2 plus sigma sub k equals 1 sub n 1 sub a sub k sub t sub k sub x, where the coefficients a sub k sub are given by a sub k sub equals 2 n, sigma sub j equals 1 sub n sub f, x sub j sub, t sub k sub, x sub j sub. Using the trigonometric definition of Chebyshev polynomials, this can be written as a sub k sub equals 2 n, sigma sub j equals 1 sub n sub f, x sub j sub, cos, k arcos, x sub j sub. 5. Reconstruct the polynomial use the calculated coefficients a sub k sub and the Chebyshev polynomials t sub k sub, x, to reconstruct the Chebyshev interpolant p, x. 4. Code example, Python, NumPy. Explanation of the code 1. Chebyshev nodes, n, kind, calculates the Chebyshev nodes, either first or second kind, given the number of nodes n. 2. Chebyshev interpolation, f, n, a, b, kind. Takes the function f, the number of nodes n, the interval a, b, and the node type kind as input. Transform x, t, and transform t, x, these helper functions transform points between the original interval a, b and the interval -1, 1. It calculates the Chebyshev nodes, evaluates the function at these nodes, and then calculates the Chebyshev coefficients. Chebyshev interpolant, t, this inner function represents the Chebyshev interpolant. Given a value t in the interval a, b, It transforms t to x in dash 1, 1, calculates the Chebyshev polynomial values, and returns the interpolated value. This is a closure, meaning it remembers the a coefficients from the outer function's scope. 3 example usage: if underscore underscore name underscore underscore equals underscore underscore main underscore underscore colon. Asterisk we define the range function, f, x, equals 1 slash, 1 plus 25 asterisk x2. This is a classic example that highlights the benefits of Chebyshev interpolation over equally spaced interpolation. Asterisk we set the interval a, b to dash 1, 1, and choose the number of nodes n equals 20. Asterisk we call Chebyshev underscore interpolation to get the interpolant. Asterisk we evaluate both the original function and the interpolant at a set of points and plot the results to visualize the approximation. V. Rational approximations. Rational approximations are functions that are ratios of two polynomials. They have the form r, x, equals p, x, slash q, x, where p, x, and q, x, are polynomials of degree m and n, respectively. Rational approximations can be more accurate than polynomial approximations, especially for functions with singularities or rapid changes. Advantages of rational approximations asterisk. Asterisk better approximation of functions with singularities asterisk rational functions can have poles, singularities, at certain points, which can be useful for approximating functions that have singularities. Asterisk faster convergence asterisk rational approximations often converge faster than polynomial approximations, meaning they require fewer terms to achieve a desired level of accuracy. Asterisk better approximation of functions with rapid changes asterisk rational functions can capture rapid changes in the function's behavior more effectively than polynomials. Methods for finding rational approximations asterisk. 1. Put approximants asterisk put approximants are rational functions where the coefficients of the numerator and denominator polynomials are chosen to match the Taylor series expansion of the function at a specific point, usually x equals 0, up to a certain order. 2. Chebyshev put approximants asterisk these combine Chebyshev polynomials and put approximations. The coefficients are chosen to minimize the error in a Chebyshev sense. 3. Reme algorithm asterisk the Reme algorithm is an iterative algorithm for finding the best rational approximation, in the minimax sense, meaning minimizing the maximum error, of a function over a given interval. This is a powerful, but more complex, approach. 4. AAA, adaptive Antulas-Anderson, algorithm asterisk a modern and effective method for rational approximation, especially useful for empirical data or black box functions where an analytical expression is not readily available. Put approximants, details. Given a function f, x, the put approximant of order m/n is a rational function r, x, equals p, x, slash q, x, where p, x, is a polynomial of degree m and q, x, is a polynomial of degree n, such that the Taylor series expansion of r, x, matches the Taylor series expansion of f, x, up to order m plus n. Steps for finding put approximants asterisk. 1. Find the Taylor series expansion asterisk calculate the Taylor series expansion of f, x, around a point, usually x equals 0. Let the Taylor series be f, x, equals c sub 0 slash sub plus c sub 1 slash sub x plus c sub 2 slash sub x sub 2 slash sub plus. 2. Set up the equations asterisk let p, x, equals a sub 0 slash sub plus a sub 1 slash sub x plus a sub m slash sub x sub m slash sub and q, x, equals b sub 0 slash sub plus b sub 1 slash sub x plus plus b sub n slash sub x sub n slash sub. Without loss of generality, we can often normalize q, x, by setting b sub 0 slash sub equals 1. We want p, x, slash q, x, equals f, x, plus o, x sub m plus n plus 1 slash sub. Which means p, x, equals q, x, asterisk f, x, plus o, x sub m plus n plus 1 slash sub. This gives us a set of linear equations to solve for the coefficients a sub I slash sub and b sub j slash sub. 3. Solve the linear system asterisk solve the linear system of equations to find the coefficients a sub I slash sub and b sub j slash sub. 4. Construct the PID approximant asterisk use the calculated coefficients to construct the PID approximant r, x, equals p, x, slash q, x. Code example, Python, NumPy, PID approximant. Explanation of the PID approximant code asterisk. 1. PID underscore approximant, f, x, m, n. Asterisk takes the function f, an array of x values x, the numerator degree m, and the denominator degree n as input. Asterisk c equals f, I, for I in range, m plus n plus 1, this line is crucial. The function f is assumed to be a callable that, when given an integer, returns the coefficient of the Taylor series expansion of the function at that order. For example, if you want to approximate cos, x, around x equals 0, f, 0, would be 1, f, 1, would be 0, f, 2, would be minus 1/2, f, 3, would be 0, and so on. Asterisk the code then sets up and solves the linear system of equations to find the denominator coefficients. Asterisk it calculates the numerator coefficients based on the denominator coefficients and the Taylor series coefficients. Asterisk it evaluates the numerator and denominator polynomials at the given x values and returns the ratio. 2. Example usage asterisk. Asterisk we define the exponential function, e sub x slash sub. The crucial part is how we define f, n. It returns the nth Taylor series coefficient. Asterisk we define the x values, the degrees of the numerator and denominator, and call PID underscore approximant. Asterisk we plot the PID approximant and the true exponential function to visualize the approximation. 6. Chebyshev PID approximation. Chebyshev PID approximants combine the advantages of Chebyshev polynomials and PID approximants. They use Chebyshev series to approximate the function and then construct a rational function that matches the Chebyshev series coefficients. This approach can provide a better approximation than either Chebyshev interpolation or PID approximation alone. Outline of the method asterisk. 1. Find the Chebyshev series expansion asterisk calculate the Chebyshev series expansion of the function f, x, on the interval -1, 1. This means finding the coefficients a sub k slash sub in the expansion. f, x, a sub 0 slash sub slash 2 plus sigma sub k equals 1 slash sub n slash sub a sub k slash sub t sub k slash sub, x. Where t sub k slash sub, x, are the Chebyshev polynomials. 2. Truncate the Chebyshev series asterisk truncate the Chebyshev series to a finite number of terms, say n terms. 3. Construct the rational approximation asterisk construct a rational function r, x, equals p, x, slash q, x, where p, x, and q, x, are polynomials of degrees m and n, respectively. Choose the coefficients of p, x, and q, x, such that the Chebyshev series expansion of r, x, matches the Chebyshev series expansion of f, x, up to a certain order. 4. Solve for the coefficients asterisk. This step typically involves solving a linear system of equations, similar to the approximant case, but using Chebyshev series coefficients instead of Taylor series coefficients. 7. Remé algorithm, outline. The Remé algorithm is a powerful iterative algorithm for finding the best rational approximation in the minimax sense. This means minimizing the maximum absolute error between the approximation and the original function over a given interval. Steps of the Remé algorithm asterisk. 1. Initialization asterisk. Choose an initial set of n plus 2 points, called the extremal set, in the interval a, b, where n equals m plus n plus 1, m is the degree of the numerator, n is the degree of the denominator. These points are often chosen to be Chebyshev nodes. 2. Solve for the approximation and error asterisk. Solve a system of n plus 2 equations to find the coefficients of the rational function r, x, equals p, x, slash q, x, and the error e such that f, x sub I slash sub, r, x sub I slash sub, equals, -1, sub I slash sub e for I equals 0, 1, n plus 1. This forces the error to alternate in sign at the extremal points. 3. Find the maximum error asterisk. Evaluate the error function e, x, equals f, x, r, x, over the entire interval a, b and find the points where the absolute value of the error is maximized. 4. Update the extremal set asterisk. Replace the current extremal set with the new set of points where the absolute value of the error is maximized. Choose the new set so that the error alternates in sign. 5. Repeat asterisk. Repeat steps 2 to 4 until the error e converges to a minimum value. Challenges of the Remé algorithm asterisk. Asterisk complexity asterisk. The Remé algorithm is more complex than other approximation methods. Asterisk convergence asterisk. The algorithm may not always converge, or it may converge slowly. Asterisk singularities asterisk. The algorithm can be sensitive to singularities in the function being approximated. 8. AAA, adaptive Antilles-Anderson, algorithm. The AAA algorithm is a more modern and generally more robust method for rational approximation than the Remé algorithm, especially when you don't have an analytical expression for the function, example when you only have data points. Key ideas behind AAA asterisk. Asterisk greedy selection of support points asterisk. AAA iteratively selects support points, interpolation points, from the domain. It chooses the points where the current approximation has the largest error. Asterisk linear least squares asterisk. At each iteration, it formulates and solves a linear least squares problem to determine the coefficients of the rational approximation. Asterisk empirical data asterisk. It works well with empirical data or black box functions, where you can evaluate the function at any point, but you don't have a closed form expression. General outline of the AAA algorithm asterisk. 1. Initialization asterisk. Start with an initial random support point or a simple approximation. 2. Error evaluation asterisk. Evaluate the current approximation error at a large number of points in the domain. 3. Support point selection asterisk. Find the point where the absolute error is the largest. Add this point to the set of support points. 4. Least squares solution asterisk. Set up and solve a linear least squares problem to find the coefficients of the rational approximation that interpolates the function values at the support points. This generally involves finding coefficients c_i such that sum, c_i asterisk f, z_i, slash, z, z_i, is a good approximation, where z_i are the support points. 5. Convergence check asterisk. If the maximum error is below a desired tolerance, stop. Otherwise, go back to step 2. Libraries and implementations asterisk. Asterisk Chebyshev, MATLAB. The Chebyshev software system provides powerful tools for working with functions, including finding Chebyshev interpolants, Chebyshev approximants, and implementing the REMA algorithm. Python libraries. While there isn't a single, readily available Python library that fully replicates Chebyshev's functionality for all of these techniques, you can find implementations of approximants and, with more effort, implement the REMA or AAA algorithms. The scipy.interpolate module has some polynomial interpolation tools that could be adapted. 9. Practical considerations and choosing the right method. Smoothness of the function. If the function is smooth, has continuous derivatives, Chebyshev interpolation or a low-order approximant might be sufficient. Singularities. If the function has singularities, rational approximations are generally better than polynomial approximations. Computational cost. Chebyshev interpolation and approximants are relatively inexpensive to compute. The REMA algorithm and AAA algorithm can be more computationally expensive, especially for high-order approximations. Error tolerance. The desired level of accuracy will influence the choice of method and the number of terms or iterations required. Availability of derivatives. Approximants require knowledge of the Taylor series coefficients, derivatives, of the function. Chebyshev interpolation only requires function values. In summary, Chebyshev interpolation and rational approximations provide powerful tools for approximating functions. Chebyshev interpolation is well suited for smooth functions, while rational approximations excel when dealing with functions with singularities or rapid changes. Understanding the properties of Chebyshev polynomials, the different methods for finding rational approximations, and the trade-offs between accuracy and computational cost will allow you to choose the most appropriate approximation technique for your specific problem. Experimentation and visualization are often key to finding the best approach.